Hi guys, so second video, we're going to talk about building functions from functions with composition, right? And basically what we're talking about with composition is we've got the same sort of premise. We've got an initial set of functions, and we're going to be creating new functions from those functions by putting functions inside of functions, right? We're going to basically say that we take one function as the input of another function, right? So right here, we've got the notation for this. This is the f circle g of x, right? And right here, this is read as f of g of x. So that little circle means of. And when we're saying f of g of x, that means that f is taking g of x as its input, right? And what we want to do here is think about what it actually means for us to name a function with function notation, right? F of x is x squared plus 4. But what is just f? F is the act of taking an input, squaring it, and then adding 4 to that, right? So that's what f does as a function. So what really function notation does is it names what we're doing to the input. If we look at k of x is 1 over 2x. But just k is the act of taking an input, multiplying that input by 2, and then dividing 1 by that value, right? That's what k is. That's what k does. If we look at g of x is the square root of x plus 1, but just g is the act of taking an input, adding 1 to it, and then taking the square root of that value. So right here, that's what all of these functions do. So when we say f of g of x, meaning that we put g of x inside f, what we're really saying here is we're applying what f is to g of x. So right here, f takes its input, squares it, and adds 4 to it. And g of x, which is the input to f now, is the square root of x plus 1, right? So immediately, this is the composition. Now, just like before, as soon as we bring our two functions together with composition this time, we are going to define the domain. So immediately what we're going to say is, what restrictions do we have for our inside function, and are there any additional restrictions that come from combining these two functions, right? So it's not like we have two separate functions that we're bringing together with an operation now. Now we've got one function inside another function, so we need to say, is the inside function going to have any restrictions? And then will the composition of the inside function and the outside function have any restrictions? And sometimes the composition is going to take restrictions away. We'll see that when we go through some of these later. But right here we've got the restriction that x cannot be less than -1 from our inside function. There's no additional restrictions that come about from the outside function, right? No denominators, no additional square roots that we need to worry about. So our domain right here is going to be from -1 to positive infinity for our composition rate. Now, when we simplify, what happens? The square and the square root cancel out. And what we end up with here is f of g of x as, right here, if we sort of take away our restriction and do a little simplifying so we can sort of see this math out. You guys can probably do this on your own, but right here, we would first cancel the square and the square root, then we get x plus 1 plus 4, which gives us x plus 5. So right here, composing these two functions gives us the linear expression x plus 5, right? And we would basically say that we would have this linear function on the domain from -1 to positive infinity, right? So right here, the composition of these two functions is a linear expression that cuts out after -1, really just like that square of the functions we saw on the last page. So right here, y-intercept of 5, so we might say 1, 2, 3, 4, 5, and then right here, we would have the ordered value, we would have the ordered pair at -1. Try to draw that in. At -1, oh, that would actually be done there, wouldn't it? and then we would go up from there. We would have a linear function looking like that. Now, right here, if you type in this expression, the composition of the two functions, if you type this guy into the calculator, that's what you would see. Obviously, if you typed in x plus 5, you would see the entire line. But right here, remember that we're saying we've got the line for the domain -1 to positive infinity here for the composition functions. Okay, so right here, what I want you guys to do is to go ahead and try these next two on your own. And again, what we're doing is, first we're composing the two functions, defining the domain, and then simplifying, right? So why don't you guys go ahead and pause the video and give these two a shot, and we will come back and look at this in a second. All right, so let's take a look at these last two compositions. For the first of the ones we had you guys try, we looked at g of f of x, right? So that's the function f of x inside g, right? So g is going to take its input, add 1 to it, and take the square root of it. So that means we're adding 1 and taking the square root of f of x, and the equation for f of x is x squared plus 4. So right here, we've got the square root of x squared plus 4 plus 1 as our composition. Now, immediately what we can say is the inside function, f of x, does not have any domain restrictions. And what we're going to see here is that the composition of these two functions is also not going to have any restrictions. So right here, our one restriction would be that this expression that's underneath our square root cannot be less than 0. So x squared plus 4 plus 1 cannot be less than 0, right? Now we might as well just sort of take down our parentheses and combine our plus 4 and our plus 1 and get plus 5, and that'll make this a little easier to see. And right here what we're seeing is x squared plus 5 cannot be less than 0. And actually, there is no x value that can make this expression less than 0. Any x value we plug in that's a negative is immediately going to be squared, so it's going to be made positive, and then we're adding 5 to that positive value. So in fact, right here, the composition does not have any restrictions, even though we've got that square root right there. And so we would say that the domain would be from negative to positive infinity for our g of f of x, and the simplified equation would basically just be us taking down those parentheses and combining the plus 4 and the plus 1 to give us plus 5 underneath that square root. All right, so our last composition is an interesting one. We've got k of x, and basically what that means is we're taking the k function and plugging it into itself. So right here, what we can say is that we would have our outside function as k, right? And if we sort of just look at what k is, that's going to be multiplying an input by 2 and then dividing 1 by that number. And then right here, when we plug k of x into k, so we take this, the k of x equals 1 over 2x. So when we plug k of x into k, we're plugging that 1 over 2x into the k function, right? And so right here, evaluating the domain restrictions, what we can say is that we know that the inside function cannot evaluate an x value of 0. That'll give us 0 in the denominator. And the composition of functions is actually not going to have any additional restrictions because there is no x value that can make 1 over 2x equal to 0, right? Plugging in 0 is, of course, going to make it undefined. And then there's no other x value we can plug in that would make this fraction equal 0. So because that can't happen, we only have the domain restriction that x cannot equal 0. So we've got our domain from negative infinity to 0, union with 0 to positive infinity. And now we can start thinking about what simplifying this expression is going to mean. So right here, what we can say is that in the denominator, we're multiplying a 2 and we're dividing a 2, right? So we can say the multiplication is going to cancel out with the division, and that's going to give us 1 over x. And now right here, a division of a fraction is equal to a multiplication of the reciprocal, so that's 1 times x over 1 over x. So right here, k of x simplifies down to just x on the domain from negative infinity to 0, union with 0 to positive infinity. And if we were to graph this guy, we would basically see that identity function, that straight line going right through the origin with a hole at 0, looking something like this. Now obviously that hole wouldn't be as large, and in fact if you graph this as our 1 over 2 times 1 over 2x, then graphing this equation right here, you probably wouldn't see the hole at all unless you went to the table like we did for that first function that was missing one ordered pair from its domain. All right, guys, so right here we are going to talk about evaluating these compositions and combinations of functions with operations for specific inputs. And we're going to talk about 2 ways of doing this. The first way we're going to talk about is just to evaluate the statement, one function at a time. So right here, we're looking first at the composition at A, right? So we've got f of g of 2, and that's telling us that we're plugging g of 2 into f. So right here, we can first evaluate g of 2. And when we do that, we're going to get the square root of 2 plus 1, which gives us the square root of 3. So we know g of 2 equals the square root of 3. Now, for our g of 2 in f, we can plug in that square root of 3 and evaluate f for the square root of 3. And that will give us the square root of 3 squared plus 4, or 7. So right here, basically what we're doing is literally interpreting what we're seeing as first g applied to 2, right? And then whatever g of 2 is gets plugged into f. So right here we've got g of 2, and then we plug that value into f, and then evaluate f for that value. So that may be one that we're most familiar with, I would say. Let's see if we can bring this down. We're going to have a little bit of trouble with that, so let's do this. Let's take this guy out, g of 3. Pull that down. Okay, so that's one method of going through and solving the composition for a particular input. So right here we'll just sort of say we found g of 2 to be the square root of 3 here, and then plug that in. The second way that we can go about this is to take that particular input out as some x value, right, and then address the composition of our two functions, simplify that expression, right, and then if our input is on the domain of that simplified expression, then we can evaluate that input for an output. Now, right here, we evaluated f of g of x on the previous page, and we found that we got the equation x plus 5 on the domain from -1 to positive infinity, right? And that came from the restriction with g. Now, right here, our input of 2 is on that domain, right? 2 is in between -1 and positive infinity. So that means that we can evaluate f of g of 2. And right here we would say f of g of 2 would be 2 plus 5, or again 7, right? So two different ways of looking at this. One thing we have to remember is if we choose to simplify first, we just have to make sure that that input is on our domain for that simplified expression. In general, right here, we already had f of g of x evaluated, right, on the previous page. If we don't have a simplified form of the equation already simplified, I think it makes the most sense to just go ahead and plug our input into our two functions separately, right? Evaluate their outputs and then combine them. So right here, when we're looking at k minus g of 3, we could go through and find what k minus g of x is and then plug in that 3. But it makes as much sense to just evaluate k of 3 and minus g of 3, right? We don't have the simplified version already, so why go through the process of simplifying and then evaluating? So right here, evaluating k of 3, we get 1 over 2 times 3 minus our g of 3 would be the square root of 3 plus 1. And that's going to give us 1/6 minus, and then right here we've got the square root of 4, which is 1/6 minus 2. And now right here we can change that 2 to 12 over 6, so we can combine our 2 and our 1/6, so that's 12 over 6 minus 1/6 gives us a negative 11 over 6 as our output. So right here, we would then say that k minus g of our 3 is our negative 11/6. Okay, so right here what we're going to do is pause the video and have you guys go ahead and try C and D on your own. It should be pretty quick work. You can use either of the methods we talked about, whatever you like better, and we'll probably just go through one way of solving to just get the answer. Okay, so pause the video now, and we will come back and take a look at this in a second. Okay, so looking at these, the way I went about it was basically just plugging in, evaluating functions individually. So right here, when I said I had g of f of negative 5, I first evaluated f of negative 5. F of negative 5 is going to be negative 5 squared plus 4, so that's 29. Then I took f of negative 5 and plugged that into g. So right here, that gave me g of 29, and g of 29 was the square root of 29 plus 1, or the square root of 30, which turns out to be approximately 5.4772. So right here we've got g of f of negative 5 as the square root of 30, or approximately 5.4772. Okay, so looking at our next one, we've got f divided by k of 3. Again, right here I said just evaluate them individually, and then combine those numbers. So right here we've got f of 3 divided by k of 3. F of 3 is 3 squared plus 4 divided by k of 3, which is 1 over 2 times 3. So 3 squared plus 4 gives us 13 in the numerator, and our 1 over 2 times 3 gives us 1/6 in the denominator. So we're dividing by a fraction, which means we can multiply by the reciprocal to get a nicer number. And right here we have 13 times 6 gives us 78, so we would say f of k of 3 would then be 78. Okay, so this is the end of the second video. We're going to come back and do one more very quick video, and then you guys will be done, and we'll do a worksheet class. So see you on the next video.